So today, when we design the overall design process, and when we do it right, when we bring sustainability into the early stages that define 80% of the overall environmental impacts, we end up having sustainable solutions in the end. And we've been looking into those sustainable solutions in my first presentation, loads of examples across all the different areas. But we also know that they create rebound effects. So how can we design differently to actually avoid those rebound effects from happening at a first instance? We can, of course, decide to just tackle them after they happen. That's what happens today. But do we have time for it? Do we have time to design new solutions that will maybe take 3, 4, 5 years to be designed, then implement them, then see the rebound effects happening, and then trying to mitigate them? The Earth might be a bit too warm when that happens. So I think we actually need to do it beforehand, and we need to bring that in the early phases of design again. And the way we propose to do it is to enable designers in the early phases to simulate how will their solution be accepted by the system, so to say. What will be the potential unintended consequences that they will bring? And on the basis of that, identify where are leverage points. Today, if you are to model those systems, it will take maybe at least a year to be able to come up with a good estimation. We don't have that time in the early stages of design, so we actually need to automate this process and to bring tools that can be used within this sweet spot during the design process. And the leverage points, as Igor just presented, will help us to test. So let's say that I have a brilliant idea of a solution that might address the rebound effect that I identified. We can test it. We can put them in the model, we can see how the model will react to it, and we can see whether they actually help solving the rebound effects, or maybe if they bring even more rebound effects, that would be terrible, right? And we can do that in the computer. We can do it by simulating, and we can do that before any material is extracted to produce that product or that product service system. And this leads us to what we aim as the final output of this project will be to create this database of what we call reboundless design strategies. So design strategies that are resilient to the occurrence of rebound effects, and that we can implement either in isolation, depending on the system that we have at hand, or in combination. At that time, we'll be able to say how much design can actually help. Can it help us in resolving 100% of the problems? Probably not. We'll probably need a combination with policies, for instance, to try to make that happen. But then we will know, and we'll have a much better idea about how to move forward on the basis of that. And when that happens, then instead of developing design sustainable solutions at the end of a design process, we will actually have reboundless solutions, which are resilient to the occurrence of rebound effects, and that will actually help us to achieve the benefits that we expect to achieve with sustainability strategies. We might not be able to get to zero, that's why I have it there. But in 5 years, we can see, and I hope that for most of the solutions, we will actually be able to do it. And this is extremely important. I mean, imagine all the money that we put into developing new products, into developing new technologies, into funding amazing research projects, if they don't actually deliver on the results. Should we really do that? And this actually will help us to have this much better idea. And when we manage to do it, then we are going to move this bar from the current state of science down to the future state of science with the development of this reboundless design theory, which will become a course at DTU in the future, so that we can actually educate designers and engineers on how to design those reboundless solutions. And by doing that, we will, of course, not only be looking into science. I mean, we need science and we need hardcore science to do it. But we also need to translate that into practice. And we need to be able to use that in our day-to-day. Otherwise, again, if it's only in a bookshelf or in a folder in your computer, it will not make any difference. So we need to bring that to industry. And we'll be working actively to get requirements and to try to understand what do you exactly need in the early phases of design so that we can deliver upon it. And at that time, we will hopefully not only be able to solve problems with those 4 social needs that we are using as test beds during the project, but also into other areas. And healthcare is actually a really big one that we see here in Denmark that we really want to work upon and maybe even apply for system projects to Reboundless so that we don't need to wait 5 years to actually start working in that area as well. And when that happens, we will actually bring one extra bubble in this graphic. This is basically representing the evolution of sustainability implementation in industry. Back then, when it started in the 70s, almost the same time that the picture from Earth was taken, companies were still having a reactive approach focused on end-of-pipe solutions, so just treating pollution after it's there, to a preventive approach in the 80s, where cleaner production actually became something really big, where we were trying to optimize our production processes to actually be able to create more output with less resources and less pollution. To a proactive approach, that's what we pray here at DTU, and that's where the world is today, looking into the whole life cycle of products and services and solutions and trying to minimize the impacts. That's where most of the efforts in relation to circular economy also are connected to bring one extra important element in here, which will be the systemic perspective based on this overall reboundless design. And by doing that and combining those 4 approaches for sustainability implementation in industry, we will hopefully be able to live within the planetary boundaries.